All right, let's take a look at the last 2 pages of your review, which focuses on our last objective, which I'll be able to solve real-world optimization problems by finding maximum and minimum values of a function over a region. So these problems, you have several steps that you'll want to follow, as you can see, that are outlined here along with the graph to help you figure out your optimal solution. So real quick, I'm going to read through the problem and we're going to get going on this. So it says, school is preparing for a trip for 400 students. Company who is providing transportation has a large bus with 50 seats and a small bus with 40 seats, but only has 9 drivers available. The rental cost for a large bus is $800 and $600 for a small bus. Calculate out how many buses of each type should be used for the trip for the least possible cost. So when I'm defining my variables right here at the very end where it says how many buses, well, what type of buses do I have? So I'm going to let X equal the number of large buses, and then I'm going to let Y equal the number of small buses. Well, then we ask ourselves, the second part here says, okay, we have a system of linear equalities. What's causing us to order buses? Well, we have a trip, or a field trip, and we got to get 400 students. So we have to have an inequality such that we get at least equal to, if not more than, 400 students, so greater than or equal to 400. Well, we get students there by ordering depending on how many buses we order. So for every large bus we order, we can get 50 students on that bus. So 50x plus, for every small bus we order, we get 40 students, so 40y. So the combination of large and small buses based on students has to be greater than 400. Now the second inequality here, they switch colors, deals with how many drivers are available. So there's only 9 drivers available. So basically something has to be less than or equal to 9. Specifically, well, only one driver can drive one bus, so the number of large buses in combination with the number of small buses has to be less than or equal to 9. Now the last 2 constraints that I ask my students to write deal with hidden constraints, meaning they're not specifically stated in the problem, but it's just kind of logical or deductive reasoning, and that is you can't have negative buses. So both x and y have to be greater than or equal to 0. So now I have my inequalities, and so it says use the graph, okay, to graph and shade the linear inequalities to find the feasible region. So remember that these two tell us that we're basically in quadrant 1. So here, okay, is my x and y axis, so I know my solution is going to be in quadrant 1. So that's kind of nice. Those are kind of graphed for us. So even to help myself here, I'm going to write large buses, since that represents x, and small buses for the y-axis. So now, one of the things that I like to do when solving inequalities is just basically 2 points determine a line. So what I like to tell my students to do is, I say, we're going to let x equal 0, and we're going to solve for y. And then I'm going to let y equal 0, and solve for x. So, I look here, for the first one, if I let x equal 0, this 50x becomes 0. So I ask myself, how many 40s go into 400? So again, I'm letting x equal 0. Well, 40 goes into 400 10 times, meaning it'd take 10 small buses to get all the kids there. Now to get the other coordinate, it'd be like saying, all right, if I don't take any, I'm going to let y equal 0, so I don't take any small buses, how many large buses would it take to get at least 400 students? So I look at how many 50s go into 400, which is 8. So I'm going to go ahead and graph that. What's nice here is I'm going to actually count these. Each square is 1, so I'll label each and every other one 2, 4, 6, 8, 10. Going up 2, 4, 6, 8, 10. So here I'm going to graph the point 0, 10, and then 8, 0. So I want to connect this. If I think about this, 10 over 8, if I reduce this, is like going 5 over 4. So that helps me get like another point to help me connect these a little bit better. I'm going to connect those. Oh, my goodness. I noticed something with my graph here. Let me just do a little eraser. Maybe you guys saw this. I kind of screwed up here, at least on my y-axis, and I'm glad I caught it. All of a sudden I'm looking at that. That should be 4. That should be 6. That should be 8. And that should be 10. Sorry, I'm glad I caught that. So I'm really looking at this 10 point. So down 5 over 4, down 5 over 4. So I can connect those nicely. That would have been a bad mistake. It says greater than or equal to, so my solution right now is going in this direction. So basically anything that's in this area right here would be possibilities. So now I do the same thing for my red inequality. So if I let x equal 0, well, if I don't order any small buses, that means I have 9 drivers. Let me rephrase. If I don't get any large buses, I can do 9 small buses. Vice versa. If I don't order any small buses, all the drivers could drive the large buses. So I could do 9 of each. So here, 0, 9, 9, 0. So I'm going to connect those together. A little off there, but that's all right. Now this one says less than, so I'm shading in this direction. So just to show you, even though it doesn't look like it, for the blue line I'm going this direction, but in the red I'm going down. So my solution set is this tiny little area right here. Just a little sliver. I don't have many choices. So now that I have it, I want to state the coordinates of the feasible region. So I want to state the vertices. There's 3 points here. So my first one here is at 8, 0. My second one's at 9, 0. This one's really nice because it intersects at the point 4, 5. I'm going to note those down. 8, 0, 9, 0, and then 4, 5. So since this is where the blue and red line are intersecting, I just want to double check, okay? 4, so I plug it in here. 5 times 4 is 200. 50 times 4 is 200. 40 times 5 is 200. 200, 200 make 400. And 4 plus 5 does equal 9. So I know that that intersection point is pretty good. Now, the next part is I need to figure out what am I trying to maximize or minimize. So I go back up to this problem here just a second. It says I want to have the least possible cost. So I'm minimizing, and it costs me $800 for a large bus and $600 for a small bus. So I'm trying to minimize my cost. or sometimes you could have put the letter C here. So my minimizing my cost, well, it's $800 for every X, for every large bus, and $600 for every small bus. So now that I have my equation here, I'm going to substitute in all of these points into this objective function. I'm going to slide this up a little bit so that we can see it a little bit better, or it's more in the middle of the screen, easier for me to write. So what I'm doing is I'm going to take these points, 8, 0, 9, 0, 4, 5. I'm going to see which one gives me the least amount of cost. So C equals 800 times 8 plus 600 times 0, that's $6,400. Well, the next one, if I actually order another bus, 800 times 9 plus 600 times 0, that's even going to cost me more money, $7,200. So I definitely don't want to do that. So here's our last one, 800 times 4 plus 600 times 5. So this is 3,200. This is 3,000. I get 6,200. So lo and behold, we're trying to minimize the cost. There's our solution. So we just write a quick sentence here. So we'll say they should order 4 large buses and 5 small buses to minimize cost at $6,200. Nice. All right, that takes care of the first example. Let's turn to the last page here. So go ahead and flip over, and let's take a look at this last example. So I go through it, basically same process. So it says, Ray volunteers to bring origami swans and giraffes to sell for a charity crafts fair. It takes her 3 minutes to make a swan and 6 minutes to make a giraffe. She plans to sell the swan for $4 each and the giraffes for $6 each. If she only has 16 pieces of origami paper and can't spend more than an hour folding, how many of each animal should Ray make to maximize the charity's profit? All right, so I'm gonna, again, we want to define our variables. How many of each animal should Ray make? So I'm gonna have X equal the number of origami swans boy, it's not liking my eyes. And then Y equals the number of origami giraffes. So now, we start to do the inequalities here. So first and foremost, it says it takes her 3 minutes to make a swan and 6 minutes to make a giraffe. Okay. Now, it also says that she can't spend more than 1 hour folding. So an hour, I need to make sure I have the same units. So an hour is 60 minutes. So the amount of minutes I spend has has to be less than or equal to 60. So it's 3 minutes for each swan. So I get 3x plus 6y for each giraffe, or 6 times y, or 6 times the number of giraffes, has to be less than 60. Now, I also know that I only have 16 pieces of origami paper. So each one takes a sheet, so the number of swans and the number of giraffes basically has to be less than or equal to 16. Of course, we have the 2 hidden ones, so x has to be greater than or equal to 0, and y has to be greater than or equal to 0. Because we can't have negative origami swans or giraffes. So now, I want to graph this. I'm hoping by now we know that this is in quadrant 1. Okay. So we know that the number of swans and the number of giraffes has to be positive. So I'm in the positive y values and positive x values. So now I'm going to do what I did before. I'm going to, for each of these equations, I'm going to let x equals 0, solve for y. And so then I'm going to also then let y equals 0 and solve for x. So on this first one, if I let x equals 0, what happens is this 3x becomes 0. How many 6's go into 60? And that is 10. Meaning if I spend all my time doing giraffes, I can make at most 10 giraffes. I do the same thing, but I'm going to let y equal 0. So, meaning if I don't use any time for giraffes, how many swans can I make? Well, 3 goes into 60 20 times. So for my x and y axis here, I'm going to actually count by 2's. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. In both directions. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So according to this, my 2 points here, I have 0, 10, so I could make at most 10 giraffes, or I could make at most 20 swans. So 10 over 20 is like saying 1 over 2. So I'm just going to go 1 over 2, 1 over 2, 1 over 2, 1 over 2. It just gives me at least a better line. I have to have less, so I'm shading below. So right now my region is this triangle. So now I'm going to graph the second inequality. So if I use all the paper for giraffes, I can make 16 of them. If I make no giraffes, I can make 16 swans. So here I go up to 0, 16, and 16, 0. 16 over 16 is 1. What's nice is I can actually graph each of the combinations here, and it's really nice because I get that nice point of intersection pretty clean. So now, here's my feasible area. Because in this case, I'm also shading down, because I have to make less than. So I get everything here in blue, red, and in the positive quadrant. So now, I need to find those corner points. Let's shift this up just a little bit. So state the coordinates, or the vertices. I have 4 of them here. So I have 0, 0. I have this point right here, which is at 0, 10. This point right here is pretty easy to find, 16,0, and the combination is 12,4. So I can check, these add up to 16, then I'm just going to check the time constraint just to make sure that's the right intersection. 3 times 12 is 36, 6 times 4 is 24, 36 and 24 does make 60, so I have that right. So now, I need to write the linear function to be maximized or minimized. But go back up here for a second. We're trying to maximize, and we get $4 for a swan, and we get $6 for a giraffe. So, and I'm trying to maximize the charity's profit. So, down here I'm going to say max profit. So I get $4 for every swan, 4x, $6 for every giraffe, y. So now I need to plug in all of these points into the equation. So if I do 0, 0, this one's the easiest. So my profit is going to simply be 0. I don't make anything. I don't have anything to sell. So the next one, I'll have 4 times 0 plus 6 times 10. Ooh, that's nice. I'm going to make $60. For the next one, I have 16, 0. So that profit is 4 times 16 plus 6 times 0. Well, 4 times 16 is 64. Anything times 0, 0. Last one, 12, 4. So I get 4 times 12 plus 6 times 4. So 4 times 12 is 48. 6 times 4 is 24. Add those together. Look at that. $72 is going to be my max profit. So, to answer the final question, Ray should make, in this case, we want to make 12 X's, which is swans, 12 swans, and the Y value was 4 giraffes, to make a profit of $72 for the charity. Excellent. That takes care of the review. Good luck to all of you on your exam.